Good evening, children. Let us continue this chapter. The trend in the Mn 2 plus bar m had discussed. Next is the trend of the conversion of Mn 2 plus to Mn M3 3 plus M2 plus to M3 plus. Right? So an examination of the zero value of M3 plus bar M2 plus value given in table 8.2 shows the varying trends. Trend is not similar. So variable trend will be it varies. The low value for scandium reflects the stability of scandium 3 plus. Okay, scandium is the first element in this row. 3D series in this series, so it has low value. It means its stability will be very high. It's low stability. Low value shows its higher stability in its oxidation state. That is the form of scandium 3 plus. The highest value for Zn is due to the removal of an electron from the stable D10 configuration of Zn2 plus. Okay, scandium has that lower value, and this Zn has a higher value, and comparatively high value for manganese shows that Mn2 plus D5 configuration is particularly stable, whereas comparatively low value for Fe shows extra stability of Fe3 plus. This variable you see in the case of that is in Zn 2 plus is stable because of its stable electronic configuration, D10 configuration. Okay, and you see manganese shows Mn2 plus. It's at D5 configuration. Okay, it is stable, and it's a low value. Whose low value ion Fe. Okay, it shows extra stability. In the beginning, it mentioned here the low value of scandium reflects the stability of scandium in 3 plus. Okay, it has that noble configuration. Highest value for Zn is due to the removal of an electron from its stable D10 configuration of Zn2 plus. So comparatively, the higher value of Mn shows that Mn2 plus. Okay, so here mentioned the values of this scandium, zinc, manganese, and iron. So Fe3 plus will be in D5 configuration. It has extra stability in this configuration. And trend in stability of higher oxidation state. Let us see. Table 8.5 shows some formulas of halides of 3D metals, and oxidation state also mentioned here. So this table shows the stable halides of 3D series of transition metals. The highest oxidation numbers are achieved in you see tetrahalide of this titanium, vanadium pentafluoride, okay, hexafluoride of chromium, and the +7 oxidation state of manganese is not represented in symbol halide, but in the case of MnO3F you see is known, and beyond Mn no metal has a trihalide except trihalide of iron, that is FeCl3, and cobalt trifluoride. Ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy. So in some cases this higher stability in their higher oxidation is due to already told due to the higher lattice energy and or higher bond enthalpy. This is the reason. Some elements of this D block or this series shows a higher stability in their higher oxidation state. Reason is very simple. Two factors. Because of two factors. One is higher lattice energy as well as higher bond enthalpy. Okay. And another feature of fluorides in their instability in the low oxidation state. that on the other hand, all copper 2 plus halide are known except the iodide. In this case, Cu2 plus oxidizes I minus to I2. Okay. However, many copper compounds are unstable in aqueous solution and undergo disproportionation. Note this point, this equation also, disproportionation of this copper 2 plus ion. What is a disproportionation? Oxidation as well as reduction of this same species. Normally oxidation and reduction undergo simultaneously, that is a redox reaction. But oxidation happens in one species, redox reaction happens in another species. But here the thing is entirely different. One species undergoes oxidation as well as reduction. This is disproportionation. Here 2Cu gives Cu2 plus plus Cu. Okay. The stability of Cu2 plus rather than Cu plus. Two oxidation states. This copper having, one is a plus 1 and a plus 2. So, this stability of Cu2 plus rather than Cu plus 1. Okay, അപ്പോൾ higher oxidation state of this copper is plus 2. In this state, it has a higher stability. It is due to much more negative hydration enthalpy of Cu2 plus than Cu plus. This sentence also very important. So, underline it. So, disproportionation of this copper and in its aqueous solution and there's a higher stability in its oxidation number, plus 2 oxidation state, etc. are very important. Highest oxidation number in the oxides, you see the table 8.6 coincides with the group number. Best example is manganese. You see manganese present in the middle, just present in 3D series. When we go through this series, when the middle approaches to middle, so the manganese shows a higher oxidation state. You see the coincidence, manganese is present in 7th group. Its a higher oxidation state is plus 7. One coincidence will come. In all cases it won't come. The ability of oxygen to stabilize the high oxidation state exceeds that of fluorine. You see the oxygen and fluorine both are higher electronegative things, elements. Actually the ability of oxygen to stabilize the high oxidation state exceeds than that of fluorine. These effect of oxygen in higher oxidation state stated elements is more than the fluorine. It means oxygen can affect the elements who has having higher oxidation state. Fluorine can also influence, but this oxygen exceeds that of this fluorine. The highest manganese fluoride is MnF4, whereas the highest oxide is Mn2O7. മനസ്സിലായോ? അപ്പോൾ ഇതിങ്ങനെയാണ് വരുന്നത്. So superiority in the covalent oxide, that is Mn2O7, each manganese is tetrahedrally surrounded by O's. Okay, Mn2O7. 2 Mn will be the 2 Mn centralized atom. This Mn will be bridged by 1 oxygen, and this Mn atom is surrounded by 3 oxygen atom. Another Mn is surrounded by 3 other oxygen atom. This is the structure. MnO Mn bridge will be there. Okay. And in the covalent oxide Mn2O7, each manganese is tetrahedrally surrounded by O's. About that much that influence happened here by this oxygen than the fluorine. Okay, so very clear. In text questions are there, we will discuss later. Classroom work it is. Chemical reactivity and E0 values. You see, transition metals vary widely in their chemical reactivity. It means we could not generalize. Many of them are sufficiently electropositive to dissolve in mineral acids. Means their reactivity towards acids are very high. Normally all the metals, especially reactive metals, that react with the mineral acids vigorously. Here also some are okay showing this vigorous reaction. Although a few are noble, that is they are unaffected by simple acids. Okay, some noble metals are here now. That is gold, platinum, and silver. The metals of first series, with the exception of copper, are relatively more reactive. Copper will not reduce. Sorry, copper will not react with this acid. Copper could not liberate H2 from mineral acids. Very before we learned that thing. Okay, except this copper, other metals almost react with noble metals. That is another thing, exception. So the E0 values of M2 plus bar M, that is the transformation from metal to metal 2 plus ion, indicate a decreasing tendency to form divalent cation across the series. Okay. About the E0 value of E0 value of this Mn2 plus bar M indicates a value it decreases. It decreases means transformation from the metal to this metal 2 plus ion is very slow, very difficult, and towards it shows very hesitancy. E0 value for manganese, nickel, and zinc are more negative than expected from general trend. E0 value will be more in these three cases. Whereas the stability of half-filled d subshell, that is D5, in manganese 2 plus and completely filled d subshell D10 configuration of zinc are related to their E0 value. You see, that contrast came here. For nickel, E0 value is related to the highest negative enthalpy of hydration. So, adangane transition metals are having very variable chemical reactivity. That is why they are showing this E0 values, varied E0 values. E0 values for the redox couple, you see M3 plus bar, M2 plus. Okay, 2 plus to 3 plus transformation. Table 8.2 shows manganese 3 plus and cobalt 3 plus. Value manganese into 1.57, for cobalt 1.97. This is the value. These are the value. So Mn 3 plus and CO 3 plus, both are in same oxidation state. They are very strongest oxidizing agent in aqueous solution. Whether the values are different, they are showing the same property. So the ions titanium 2 plus, vanadium 2 plus, and chromium 2 plus are strong reducing agent. You see, Mn 3 plus and cobalt 3 plus, you see, they are at 3 plus state now. So they are the strongest oxidizing agent. Here 2 plus ionic form of this titanium, vanadium, and chromium, they are strong reducing agents. Will liberate hydrogen ion from dilute acid. Okay, its equation is here. Some more important questions are given here. Two in-text questions also. Which is a stronger reducing agent, Cr2 plus or Fe2 plus, and why? Okay, so making us little troublesome questions. That much thorough knowledge of this chemical E0 values, enthalpy, and the trend towards this Mn 3 plus bar, Mn 2 plus, Mn 2 plus bar M, that tendency and these things must be. So at least you must be able to explain with the help of 2-3 sentences. Okay. And one of the important or major property of these D block elements are magnetic properties. When a magnetic field is applied to substances, mainly two types of magnetic behavior are observed, like diamagnetism and paramagnetism. From the chapter, that is Unit 1 Solid, we learned this thing. Diamagnetic substances are repelled by applied field, magnetic field, while these paramagnetic substances are attracted. Substances which are attracted very strongly are said to be ferromagnetic. paramagnetic, diamagnetic, ferromagnetic. Substances will be attracted towards in the presence of magnetic field is paramagnetic, repulsion is there, so it is diamagnetic. More attractive force showed, that is ferromagnetic. Okay, many of transition metals ions are paramagnetic. They will show the magnetic property. It means paramagnetism reason arises from the presence of unpaired electrons. More the number of unpaired electron, that metal will show more magnetic property. The electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. Spin. So you see, pair of electrons will rotate clockwise and anti-clockwise. Any body, any object, when it rotates and spin itself, so it has one angular momentum. That phenomenon will be the, you're physics students now, you know this thing. For the compounds of this first series of transition metal, the contribution of orbital angular momentum is effectively quenched, and hence it is of no significance. For this, magnetic moment is determined by the number of unpaired electrons. Simply, some transition elements are showing magnetic property due to the presence of unpaired electron. Only this much. Okay. Actually, unpaired electrons are determining this magnetic property and is calculated by using spin-only formula, that is mu equal to root n into n plus 2 mu. N is the number of unpaired electron. Nu is the magnetic moment in unit of Bohr magneton, that is Bm. Okay, and number of unpaired electrons you have to learn. You see the table 8.7. ഇത് പഠിക്കണം. Definitely you have to learn this thing. And that is the number of unpaired electron. Numericals anyhow will come. So they used to mention, you see the example, calculate the magnetic moment of divalent ion in aqueous solution of its atomic number is 25. They won't mention the name of that particular that element, that metal. Atomic number only they will give, that is 25. 25 has given here. Okay, so the divalent ion in aqueous solution will have D5 configuration. You write the configuration 1:2:2, 2p6, like that. Okay, so 5 unpaired electron will be there. So the magnetic moment in mu is equal to, okay, D5 configuration, so unpaired electron will be 5. This is okay. Atomic number 25, which element it is? You see the series, atomic number, and its configuration you learn, and number of unpaired electron, and substitute the values to this equation. Okay, another in text question, you see that calculate the spin only magnetic moment of M2 plus atomic number is 27. Atomic number is 27 means which element will be? Nokike. You see which element it is. Atomic number 27. Copper maybe, right? You keep 27 is cobalt, it is cobalt. 25 is manganese. So you have to, so scandium 21, you study the order of that element. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. It starts from 21 to 30. You have to learn this thing. In text question we will do in our classroom. Formation of colored ion, that is another property of this d block element. When an electron from lower energy, that is d orbital, is excited to a higher energy d orbital. How many d orbitals are there? 10 d orbitals will be there. S is 2, P is 6, D is 10, like that it goes. So, learned from 11th class. The you have to recollect these things. Okay, and the lower energy leveled d orbitals and higher energy level d orbitals will be there. So when an electron excited from lower d orbital to higher d orbital, the energy of excitation corresponds to the frequency of light absorbed. Okay, when we expose certain elements in this sunlight or some light, so this element will absorb the visible light or the colored light from this specific area, and this electron gets extra energy and it starts excitation. When these these electrons excited, this colored, that particular colored rays will be emitted out. That is why it shows color. The frequency generally lies in the visible region. Okay, and frequency of the light absorbed is determined by the nature of this ligand. Okay, in aqueous solution where water molecules are the ligand, aqueous molecules means you see copper sulfate crystal, CuSO4.5H2O. Ligands are five molecules of water. But depend upon the nature of these ligands, they will absorb a particular colored area from this visible rays and it emits. Okay, hydrated these cupric ions absorb red light and it shows which color? That is blue color, greenish blue color. Okay, in titanium hexahydrated titanium 3 plus ion. Okay, it's a configuration and it absorbs yellow, but the solution will be in pinkish color. Okay, purple color, pinkish purple color. And scandium 2 plus, titanium 2 plus, mercury 2 plus, cadmium 2 plus, zinc 2 plus does not have unpaired electron, so it will not absorb, so their compound will not show particular color. അതൊക്കെ ഇവിടെ ടേബിളിൽ യൂസ് ചെയ്ത ടേബിൾ 8.8. And one more property is the formation of complex compound. Complex compounds are those in which the metal ion bind a number of anions or neutral molecule giving complex species. Okay, complex compounds are formed. Complex compounds means the centralized metal atom is surrounded by some complex ions, group of ions. Examples here: FeCN6 minus ion, that is 6 Cn molecule will be surrounding this Fe. Centralized atom is Fe, metal atom is Fe. So it could bind 6 cyanide molecule at a time. Okay, and 4 minus form of ion also, and CuNH3 4 2 plus and PtCl4 2 plus examples for complex ions. Okay, the transition metals form a large number of complex compounds. One of the important, and the reason this is due to the comparatively smaller size of the metal ion. Okay, their high ionic charges and the availability of d orbitals for bond formation. Availability of d orbitals means, suppose 3 families are coming to your home as guest. You have to provide 3 rooms, guest rooms. Am I correct? If you don't have these 3 separate rooms, you could not give accommodation to these 3 families. Those who are having this much rooms, they will invite and they will make a bond with these families and they could accommodate these families at a time. Exactly like that, some coordination compounds have number of d orbitals, no? Empty d orbitals. So these d orbitals are the space for the occupancy of these ligands. Okay, tetracarbonyl nickel, it is a complex ion. So nickel could accommodate 4 CO group at a time because of empty 4d orbitals it has. That is why. Another property is catalytic property. Ligands and the formation of complex compounds will learn deeply, widely in the chapter coordination compound. കേട്ടോ, സൂപ്പർഫിഷ്യലായിട്ട് നമ്മൾ പോവാണ് ഇൻ ദിസ് ചാപ്റ്റർ. ദ പ്രോപ്പർട്ടി ഓൺലി വി ആർ ഡിസ്കസിങ്, പ്രോപ്പർട്ടി ഓഫ് ദീസ് ഡി ബ്ലോക്ക് എലമെൻറ്റ്സ്. കേട്ടോ, catalytic property. Catalytic property means they are good catalyst. Very before I told you, vanadium pentoxide in contact process we are using, oxide of vanadium. In Haber process, finely divided iron. It is the member of D block element. And catalyst at a solid surface involve formation of bonds between reactant molecule. You see atoms of so the surface is the platform for accommodating these ligands properly. It makes a platform, it makes a space for attaching. Iron is the vanadium, platinum, etc. are the members of this same D block. Transition elements, they are transition elements. So zinc will not, because we are not considering this zinc, mercury, etc. as D block elements, but this iron, vanadium and this platinum, etc., because they are having surface, a good platform for providing or for attaching this species on its surface. That is why they are acting as a good catalyst. These catalysts are providing lower activation energy. They have to lower this activation energy. Otherwise, they are providing very low activation energy. That is why the chemical reaction proceeds rapidly and we will get the product in accordance. Okay, this has effect of increasing the concentration of reactants at the catalyst surface, also weakening the bonds in the reacting molecules, thereby lowering this activation energy. Also because the bond between these reactant molecules must be weakened. So catalyst does this thing. By weakening this bond, metallic whatever, this reactant bonds must be weakened. Then only it breaks and very soon they could react with other reactants to form products. Intermediate compound will be formed. So these kind of things will be happen or undergoing on the surface of this particular catalyst. So this catalyst provides very lower activation energy. Then only this bond will break. Okay, the bond between these species, reactant species, will be weakening, and at last it breaks and forms, undergoes this chemical reaction and forms the product. And another thing also, because the transition metal ions can change their oxidation state. They are having variable oxidation state. Very before we discussed, they become more effective as catalyst. So due to their variable oxidation state, they can vary their oxidation state. So and that is the main reason, one of the main reason for acting as a catalyst. Okay, formation of interstitial compound. Interstitial compound means are those which are formed when small atoms like hydrogen, carbon, nitrogen are trapped inside the crystal lattice of matter. So D block elements or transition metals are having interstitial space. Interstitial space means the space between the particles. Okay, so the small atoms of this hydrogen, carbon or nitrogen can be occupy the space between these the atoms of this metal. Okay, so they could occupy the space between these atoms, between these particles. Okay, we can call this space as interstitial space, and small atoms could be accommodated, okay, in this space. So because of the nature of their composition, these compounds are referred to as interstitial compound. and their chemical characteristics. There are 4 chemical characteristics. They have high melting point, okay, higher than those of pure metal after the formation of interstitial compound ട്ടോ. And they are very hard. Some borides approach diamond in hardness. ചില ബോറൈഡ്സ് ഉണ്ട്, ഡൈബോറൈൻ എന്നൊക്കെ പറയുന്ന പോലെ. So their hardness will actually, the hardest substance ever known is our diamond. But some boranes are some metallic borane. Metal borane means metal from these transition elements. So their boranes will be, their hardness will be around the hardness of this our diamond. Third property is they retain metallic conductivity. Okay, they are chemically inert. These are the properties of interstitial compound. Another important property is alloy formation. So approximately 5 or 6 important properties are discussed. Alloy is the mixture of the alloys may be homogeneous solid solution, homogeneous mixture of metal with metal or metal with a non-metal. We know this thing because of similar radii and other characteristics of transition metals. Almost all the metals are having similar atomic radius or atomic sizes. No, that is a trend from left to right in series. So alloy formation is readily undergoing, and the alloys so formed are very hard, have often high melting point. Brass is the mixture of copper and zinc, both are present in the same group, and not group, that D block. And bronze, you see, copper and tin, both are present in this D block. Industrially importance is the stainless steel. I told you Fe, that is iron, chromium, nickel and carbon will be the mixture of these elements of they are the members of transition elements. Okay, in text questions are there. Explain why Cu plus ion is not stable in aqueous solution. Because of its property of disproportionation in aqueous solution. It will disproportionate. It will undergo oxidation as well as reduction simultaneously. അപ്പോൾ അത് പഠിക്കണം. നെക്സ്റ്റ് ടോപ്പിക് ഈസ് ഡിലീറ്റഡ് some important compounds of transition elements. Potassium dichromate and potassium permanganate. God's grace, that avoided because its preparation, its chemical reactivity and structure എല്ലാം. സോ എൻ്റെ ഈ പറയുന്ന പോലെ ഓക്സിഡൈസിങ് റിയാക്ഷൻസ് ഓഫ് KMnO4 ആൻഡ് അതൊക്കെ ഇമ്പോർട്ടൻ്റ് ആയിരുന്നു, ബട്ട് ഫോർച്ചുനേറ്റ്ലി അവോയ്ഡഡ്. Okay, one more session is there, that is inner this is a D block element, transition metals, transition elements, it is over. Next we are going to inner transition elements, that is F block elements. The at the bottom, extreme bottom of this periodic table, 2 rows will be there, each rows consisting of 14 elements. Okay, this lanthanoids and actinoids. Okay, lanthanum to angana varuna starts from lanthanum, that is lanthanoids. All the elements present in this row called as lanthanoids, and actinium, from actinium the left elements are also called as actinoids. Okay, we will discuss it.